Hello students, in this video lecture we are going to see about architecture of 8086. Let's go into our subject. Let's go into the architecture of 8086. 8086 is a 16-bit microprocessor which is being launched in 1978 by Intel. It is said to be a 16-bit microprocessor. A microprocessor is said to be as 8-bit, 16-bit or 32-bit by the number of data bus what they have. In this case, in our 8086, we have 16-bit data bus, hence it is said to be as 16-bit microprocessor. This 8086 can address around 20-bit memory address. It can address 20-bit memory location. It can address 20-bit memory location. That is, the total size what it can address is 2 power 20, which is equal to 1 MB. Right? In our 8086 architecture, we have multiplexed mode of addressing. That is, we have 16-bit data bus and we have 20-bit address bus. What we are doing is that A, D, not. This indicates that this is a multiplexed where it is being used for address and also for its data bus. That is from 0 to 16, 0 to 15, which is nothing but 16 is a count which is used for addressing both data bus and address bus, which is in the multiplexed mode, and A16 to A18 is a dedicated thing for our address bus. It can support 64K for input output ports. Now, let's go into the architecture of 8086. This 8086 consists of two sections. That is, execution unit is one section and bus interface unit is one section. Now let's see what this bus interface unit is going to do. Bus interface unit is one which is going to read, write all the operation. That is, if you want to read with the my memory interface, it is going to help you in reading. If you want to write, it will be helping in reading. In the other case, if you want to operate with any of the input output port, the same operation can be done by our bus interface unit. Now, execution unit. Execution unit is one where all the instructions are being decoded and it divides the work between the execution unit and also your bus interface unit. If you need anything with respect to addressing, then it will be that job will be given to bus interface unit, and if anything which is dealing with, say, for any arithmetical operation, then that will be dealt by your execution unit. Now let's see in detail about this execution unit. This execution unit consists of following parts. They are instruction decoder. This is our instruction decoder. Then control system. This is our control system. Then ALU is nothing but arithmetical logical unit. Then flag register. Then pointers and instructors. Then pointers and instructors, and also we have general purpose register. This are our general purpose register. This is our pointers. There are two pointers, stack pointer and base pointer. Then index registers, we have two index registers. They are source index registers and destination index registers. Now, let's see in detail about all the parts in our execution unit. That is, in the work of instruction decoder is to translate the instruction from the memory. Whatever instruction we are getting from the memory will be sent to our instruction decoder, where it will decode and find what its operation is. That is the work of our instruction decoder. Then control system. Control system which generates the timing. Then it performs the operation. Whatever operation you need, that will be performed by our control system. Then let's see about ALU, which is nothing but arithmetical logical unit, which performs all the arithmetical or mathematical related job. That is, say for example, if you want to do addition, subtraction, multiplication, division, shifting, any kind of work will be done by your arithmetical logical unit. Then let's come to general purpose register. This is our arithmetical ALU, and this 8 are our general purpose registers. They are AL, AH, BH, BL, CH, CL, DH, DL. These are our general purpose register. This general purpose register can be used either as a 8-bit or as 16-bit. So that is, if you want to use this AH alone, it is 8-bit. If you want to use it as 16-bit, then we will be addressing the same as AX. Right? In the same way, BH, BL. This is one 8-bit, this is one 8-bit. right? Now let's see the special work of our general purpose register. AX is mainly used for the arithmetical logical operation, then BX is used for the memory operations, right? That is for address related thing. Then CX is used for counting, shifting, those kind of operations. This DX register is used mainly for the operations during multiplication and division. Now let's go to the flag register. This is our flag register. This register is very much used. That is, this register consists of 16. This is a 16-bit register where in which we are going to use only 9 active flags. That is, out of 16, we are going to use only 9 active flags. That is 6 for a condition and 3 for control. That is, say for example, if I am going to do any arithmetical operation, if I am having any carry, then automatically this carry flag, that is a bit which is allotted for a carry flag, will be set to 1. Else it will be 0. So if I want to find whether my operation is having carry or not, then automatically I will be checking my carry. If my carry is 1, that says that my operation is having carry. In the same way, we have 0 flag, we have sign flag, we have overflow flag, everything for a specific operation. Now next is a control flag. This or trap flag, IF is an interrupt flag. These two flags are used for interrupts operation, and the DF is the direction flag. In any case, we are going to perform rotation, left rotation, shift rotation. Sorry, if we are going to do any shifting operation or any rotating operation, we need to shift. So in that case, the direction of shift can be known by the directional flag. Now let's go to the pointer register. The pointers registers are stack pointer and base pointer. As of now, we have seen about the special function registers, we have seen about the instruction decoders, we have seen about the control system, right? We have seen arithmetical logic unit. Now the last one is our stack pointer and base pointer. This is used very much in the stack segment. That is, in the stack segment, if you want to know where is the stack location, that is data within the stack segment, we can know by using this base pointer, and the specific location can be known by the SP, that is stack pointer. Now let's go to the source index. Source index holds the value where the data is used in the case of arithmetic operations. Data index, destination index is one this is destination index. This destination index is going to store the value of string which is going to act as a destination. Now let's go to the top portion, that is bus interface unit. This bus interface unit have 3 sections, that is instruction queue. This is nothing but instruction queue. This uses the pipelining concept which I will explain you. Then segmentation registers. These are all this 4 are our segmentation register. Then address computation engine. This is our address computation engine. This is the memory interface, which is the external memory interface which we are going to address. Right? Now let's come to the instruction queue. Instruction queue is one where we have which can store about 6 instructions. That is, while taking a data from a memory, that is while taking the instructions, if the 6 instructions will be stored in our instruction queue. This is something like our pipelining concept where our processor don't have to wait for the next instruction to be fetched from the memory interface. It can directly take it from the instructions queue. By this, the accessing time can be very much reduced. The problem in this is that when we have jump statement, in that case only the instructions will not come in order. In that case, the instruction queue will be refilled again. Right? This is about our instruction queue. It uses parallel processing. It uses 6 instructions at a time. Instruction is queued in, first out. Whichever is getting first will be going out. Right? In other words, the instruction queue permit to store in advance a specific instruction that will be executed in future. This is a very good word. That is very good statement. That is, instruction queue permit to store in advance. That is, say for example, if I have 7 line of program. If my first line is getting executed here, then automatically my 6 instructions will be stored in my instruction queue. Right? Now let's go to the segmentation registers. These segmentation registers are used to address the memory space. Right? So the following are our segmentation registers. Code segment, where our code is going to be stored. Stack segment is nothing but our stack. Data segment, our data is going to be stored. And the extra segment is there for extra operations. Right. In other words, about the segmentation registers is used that it is used to calculate the address within the 1 MB of memory space. Now, what is this 1 MB of memory space? Our microprocessor can address around 1 MB of memory space. That is, it has 5 bit, which is nothing but 20 bits. Sorry, it has 20 bits which can address around 1 MB. That is the reason 2 power 20 is 1 MB. That is the reason it can address 20 MB. Now, let's come to the address computation engine. Now, we have this address computation engine mainly used for converting the 16 bit to 20 bit. All the registers, whatever we have in our microprocessor are 16 bit. But the addressing of memory interface, that address is going to be 20 bit. I will repeat again. These registers are 16 bit and the memory interface, this address is going to be 20 bit. Now what we have to do is that I have to convert my 16 bit into 20 bit so that I can address my memory interface. So what I am going to do, this computation engine converts logical address, which is nothing but 16 bit, that held by the segmentation register. These are all the segmentation registers, into physical address. Physical address is going to be 20 bit. That is 16 bit address to 20 bit address. How it is doing? Now let's see here. Now I can have my segmentation segments anywhere. I can have my stack segment here, or I can have wherever it is. The length of my stack segment is 64K. How it is 64K is that 2 power 16 will give me the total space that my stack segment can have. Right? In the same way, code segment have 64K, then data segment 64K, extra segment is going to be 64K. My total memory is going to be 1 MB, which is nothing but 2 power 20. Now let's go to the how my address computation engine is working. Now before going to that, we should know what is instruction pointer. My instruction pointer is going to point where my instruction is now, right? That is, my code segment has the code, what are all the code I have, and instruction pointer is going to say in my code segment where is my instruction right now. That is, say for example, I am just taking right now my code segment is 348A hex. Right? Now, my instruction pointer is going to point 4214. Now, in order to convert to 20 bit, what I have to do is that I have to append a 0 to my code segment, where CS into 10. I am appending a 0 to my code segment, and then I am adding my IP address, instruction pointer. It is instruction pointer. Now, my physical address, 0 plus 4 is going to be 4, A plus 1 is going to be B with respect to hexa, then 8 plus 2 is going to be 10, 10 is nothing but A, 4 plus 4 is 8, 3. So now I got my physical address, which is 20 bit, right? So this is how it is calculated. I have shown it graphically. That is, now if I have this is my code section where it is going to start, and I have added with my physical IP address. So in this code segment, my IP address is going to point out a particular location so that it will point here. Right? I'll repeat again. The whole section is my code segment, which I have shown you, right? Out of which, to know where it is executing now, you can know that by using this instruction pointer. Now we have discussed about all the components in our microprocessor 8086.